Hi, my name is Roy Hurley. I'm a student of engineering at Lancaster University, currently studying for my bachelor's in mechanical engineering through Blackpool and Fylde College. And in this video, I'm going to talk to you about nuclear thermal propulsion for space exploration, and more specifically, nuclear thermal rockets. So the aims and objectives of the research performed and also this video are to show how an NTR generates energy for propulsion, understand the benefits of a nuclear thermal propulsion system, have a brief look at some historical NTR research, gain an understanding of the fuel elements used in a nuclear reactor for NTRs, and have a quick look at some thermal hydraulic considerations in NTR designs. Now, nuclear thermal rocket, it uses nuclear fission, which is the separation of uranium atoms to create heat energy. That heat energy is then transferred to a medium. The medium then goes on to generate propulsion. So we can think of an NTR as essentially a heat exchange engine. It uses hydrogen as the medium for heat exchange. On this slide we can see two examples of NTR design, a radial flow and an axial flow. Where the two differ is the flow path of the hydrogen through the reactor core. But essentially they generate propulsion in very similar ways. Hydrogen being used as the medium for heat exchange starts its life as a liquid at approximately 20 Kelvin and is pumped firstly to the rocket nozzle. It follows coolant channels around the extremities of the rocket, passing over the shear wall and onward towards the reactor core. The reason for this is to maintain temperature. At this point, the hydrogen is used as a coolant. But as the hydrogen reaches the reactor core, it's expected to have accomplished temperatures of approximately 400 Kelvin. Now, at that kind of temperature, the hydrogen is starting to change to, or may have possibly already changed to, a gas from its liquid state. Now, at the reactor core, this is where the two designs differ in terms of flow path. Axially, the hydrogen will flow through hot gas channels that run the full length of the fuel rods, and the radial flow design, the hydrogen will flow around what's called a particle bed or a pebble bed, depending on fuel element size, inward towards a hot gas channel, which is in the center, and then change direction axially to flow out towards the rocket nozzle. Now, in both designs, as the hydrogen passes through the hot gas channels, the temperature of that hydrogen is expected to accomplish up to 3000 Kelvin. Now, reaching those kind of temperatures, the hydrogen gas is obviously superheated and gets really excited. That excited gas accelerates and gets compressed in the convergent-divergent nozzle, which essentially causes the propulsion of the system. So, simplified, specific impulse is the thrust per mass flow rate of the propellant, and it essentially defines the efficiency of the rocket system. Now, NTRs have the potential to generate twice the specific impulse as a chemical rocket, and this is mainly down to the fact that it uses hydrogen as a propellant. Now, hydrogen is the lightest element on the periodic table, meaning it has much less mass than the chemicals used in today's rockets. Because it has much less mass, it has a much lower mass flow rate. This means that there is a potential for a reduction in propellant requirements per mission, because the total mass of the rocket is lowered thanks to the propellant mass being lower than that of chemical rockets. Also means the scope to increase payload and get the same amount of efficiency from an NTR as a chemical rocket, but have the benefits of being able to take greater payloads on missions. That increase in payload mass could be converted to an increase of propellant mass, meaning we could take more propellant, which could be used for longer burn times to generate more direct flight paths, all meaning that it could shorten mission times. Now, shortened mission times has the benefits in terms of safety for the astronauts on that rocket. So less time spent in space means the less amount of cosmic radiation and other hazards the astronauts are exposed to. So nuclear thermal propulsion and nuclear thermal rockets aren't a new concept to us. They've been researched extensively over many years by organisations all around the world. But NASA have had the most recorded amount of success with their research. That was under the Rover and NERVA program, NERVA standing for Nuclear Engine Rocket for Vehicle Application. They started their research in 1946 under the Rover program, and the Rover program looked at different concepts of nuclear thermal propulsion. Now, over that period of time, they started to focus their research into nuclear thermal rockets. That nuclear thermal rocket research was then put under the new NERVA program up until 1974. Just under the NERVA program alone, there was 20 prototypes tested, all with varying levels of success. One nuclear thermal rocket deemed flight ready, that was called the NERVA XE prime. That NERVA XE prime was thought at the time that it could possibly go onto an Apollo mission. But due to lack of government interest at the time and other political issues going on, that never came about. Now, at this point, you're probably thinking to yourself, well, we know nuclear thermal rockets are more efficient because they've got twice the specific impulse. We have access to proved designs that work as a rocket engine. Why can't we use them now? Well, the designs that were developed under the Rover NERVA program all used what was called highly enriched uranium fuel elements. Now, highly enriched uranium is not legal for civil use because it's classed as a weaponizable material. These days, nuclear reactors were only allowed to use low enriched uranium fuel elements. So the difference between the HEU and the LE fuel elements is the concentration of uranium-235 within those elements. Now, those elements can either be come in the form of a rod or a particle or a pebble, depending on the reactor design, but essentially the classification of the fuel element, whether it be HEU or LEU, is still the same. Highly enriched uranium is about 95% uranium-235, where low enriched uranium has a concentration of equal to or less than 20% of uranium-235. Now, the remainder of the fuel element will be uranium-238. Now, natural uranium ore, as we dig it out of the ground as a rock, is 99.3% uranium-238, and 0.7% of that rock is uranium-235. Now, uranium-235 is a readily fissile material. That's why it was favoured back in the NERVA program. But it also makes it highly reactive and potentially dangerous. So uranium-238 is used. Now, uranium-238 is classed as a non-fissile material. It will become fissile through beta decay. So an ideal reactor environment is known as critical, or K equals 1. This is where from generation to generation only one neutron from the sum of neutrons emitted goes on to react with another atom. If K is equal to more than 1, the environment is known as supercritical. This means that the reaction rate is increasing and could potentially increase exponentially. If K is equal to less than 1, the environment is known as subcritical, which means that the reaction rate is slowing and could eventually stall or stop. The K effective number is the K number with the neutron loss factored in. Now, if we put an LEU fuel directly into a design that's designed to take HEU fuels, what we find is the reaction environment becomes subcritical, meaning that the reaction rate is a lot lower and the reactor cannot maintain reaction rate. This is down to the fact that LEU fuel has less fissionable material in its element, less uranium-235. So the way to get around this, we could simply throw more fuel in, more LEU fuel, but this has a negative effect because by putting more fuel elements into the reactor, you're increasing the reactor mass, and therefore will have an effect on the efficiency of the system specific impulse. Another solution could be to improve neutron economy. Now, the way improving neutron economy is achieved is by using different moderator materials. Materials such as ceramic metallics or cermet as a moderator rather than a graphite, which could potentially create a better environment for the lower enriched uranium. So, thermal hydraulic considerations in NTRs, we concern ourselves with temperature, pressure and flow. Where there's a change in temperature, there's a change in pressure, there's a change in flow. Or we can say, where there's a change in one, there will be a change in all. The issues presented through thermal hydraulic considerations could be heat flux or hot spots in the reactor core, a pressure drop of the hydrogen, or flow shift, typically seen in radial flow designs. The image presented is of a single fuel rod taken from a Korean NTR known as the Kanuta LEU NTR. It's an axial flow design, so the hydrogen runs the length of the fuel rod. And in order to combat the issues of heat flux and pressure drop, they've incorporated a square lattice geometry throughout the length of that fuel rod. And what that square lattice geometry does is controls the flow of the hydrogen, enabling as much heat to be exchanged from that fuel rod to the medium, flowing through that fuel rod. Also, the control of the flow helps reduce the amount of pressure drop as the hydrogen accelerates through the length of that fuel rod. So PBRs, or particle bed reactors, are radial flow reactors. An equal pressure drop axially across the particle bed and a uniform distribution through the particle bed is considered to be an ideal pressure profile. Now, the fuel elements are sandwiched between frits. There's a hot side and there's a cold side, the hot side being the side of the hot gas channel. So if we look at the simplified 2D PBR core and the axial pressure profile, they both show the flow shift axially in the PBR core. The axial pressure profile shows a significant drop in pressure on the hot side or in the hot gas channel. This is due to the acceleration of the hydrogen as it heats up, increases in velocity. On the other side, on the cold side, the cold frit, there is a slight increase in pressure. This is due to the conversion of dynamic to static pressure. Now, the pressure drop causes a disproportionate distribution of fluid flow into the reactor core, or also known as flow shift. This creates hotspots in the core bed. Now, there's two ways to combat this. One of them is to optimize the hot and cold frits to control the flow radially across the particle bed, or we can optimize the diameter of the hot gas channel. This will help prevent substantial pressure drop while maintaining fluid velocity. So, in summary, thanks to the Rover Nerva program, there's a wealth of data and designs there for engineers to reference and help understand what is achievable from nuclear thermal propulsion and nuclear thermal rockets. We understand twice the specific impulse is achievable from a nuclear thermal rocket as opposed to a chemical rocket. LEU fuels can be used in NTRs just by optimizing the moderator materials used within those reactors. And also, thanks to modern tools such as CFD, we are able to optimize thermal hydraulic considerations and solve those problems that arise through design. This leads me to believe that nuclear thermal rockets are a viable option for space exploration, and quite possibly we will see them in the not too distant future. Thank you for watching. I hope you found that informative. If you've got any questions or you think I'm wrong on any of my facts, please put them in the comments and I will try and answer them as soon as I can.